Okay, in the previous video, we tried to answer this question, and we did answer it. What's the vapor pressure of seawater at a certain temperature? We came up with this answer, 0.0226 atmospheres, and we compared this to pure water, which is not seawater, at the same temperature, and the vapor pressure of seawater is lower than the vapor pressure of pure water. And the reason is because we have other things other than water mixed in with seawater. Basically, we have table salt, and table salt doesn't make a vapor at these temperatures. In fact, you have to get really, really hot, much, much higher than boiling point of water to get the vapor pressure of these things above zero. So as far as we are concerned, sodium and chloride ions, they have a vapor pressure of zero at most of the temperatures that we will ever see. And because they don't form a vapor, they basically dilute the amount of water, and if they dilute the amount of water, the vapor from the water goes down. So the vapor pressure of water is down. And so the larger point that I'm trying to make here is that if we make a table, pure water, seawater, and we have temperature over here. At 20 degrees Celsius, the vapor pressure of pure water is 0.0231 atm, or atmospheres. The vapor pressure of seawater is 0.0226 atm. So the seawater vapor pressure is lower, right? This is a lower number than that one. And this is going to be true for any temperature that we pick for seawater. If we pick 40 degrees Celsius, I don't know what the number will be, but this will be some number of amount of vapor pressure, some number of atm, and this will be some lower number. The vapor pressure will always be lower in seawater because we have these sodiums and chlorides that don't give you any vapor pressure at all. And the point that I want to make here is that there's something special that happens at 100 degrees Celsius. If you remember, water boils at 100 degrees Celsius, and our definition of boiling point is that for boiling point, the vapor pressure of the liquid has to be equal to the outside pressure. So we know that for pure water at 100 degrees Celsius, the vapor pressure has to be 1 atm because the outside pressure at sea level is 1 atm. What this means is if we have seawater at 1 atmosphere of pressure, the vapor pressure is lower than 1 atm. And what that means is seawater will not boil at 100 degrees Celsius because it doesn't have enough vapor pressure to do it. And again, just to say this in a slightly different way, boiling point of seawater is higher than 100 degrees Celsius. It's higher than the boiling point for pure water because seawater just doesn't have as much vapor pressure as pure water at whatever temperature you pick. The other thing that I want to point out, and I pointed this out in the previous video, is that it doesn't really matter what you dissolve in the water. We picked something that everybody's pretty familiar with, table salt dissolved in water. But as long as the stuff that you throw into the water doesn't form a vapor, then you'll have the same effect. If you throw sugar, which doesn't really have a vapor, into water and dissolve it, it will lower the vapor pressure of water, and it will make the boiling point of sugar water be higher than the boiling point of regular water. And there's a special name for this. Whenever you have something that has an effect in chemistry, but it doesn't matter what the material is, it just matters how much of it you threw in, that's called a colligative effect. So just to kind of give you a specific example, sodium and chloride ions have a colligative effect on the boiling point of water, or they have a colligative effect on the vapor pressure of water. In other words, it doesn't really matter that it's sodium and chloride. I could have picked other things that don't have a vapor pressure, but if I throw more and more of those things in, I have more and more of an effect on vapor pressure. That's called a colligative effect. And if you notice, just to emphasize this, I threw in a certain amount, 0.56 moles of sodium ions and chloride ions into our pretend seawater. But if I threw more of them in, if I threw larger amounts in, then basically they would reduce the vapor pressure of water even more. And again, that's called a colligative effect. And I want to show you a little bit more of what's happening with colligative effects and vapor pressure on the next slide. This is a phase diagram for water. So you've seen this before. There's temperature on the x-axis. There's vapor pressure or just pressure in atmospheres on the y-axis. And this line here and this curved line here is basically the vapor pressure of liquid water at different temperatures. And what that amounts to is this is the boiling point line. And what I'm showing you is the phase diagram for pure water. And this is the freezing melting line over here. And this is 1 atmosphere. So this is the external air pressure that we are most accustomed to. And so if you said, what's the boiling point of pure water? Well, it's 100 degrees Celsius, because if I pick a temperature of 100 degrees Celsius for water, the vapor pressure of my pure water is going to equal 1 atmosphere, and that's the outside pressure. And that means that it will have just enough pressure to start to boil away. Oh, and this is the freezing point. So if I pick 0 degrees Celsius for my water, basically this is and 1 atmosphere of pressure, water will begin to freeze and melt at 0 degrees Celsius. But if I start to throw table salt into my pure water, it's not pure anymore. And you remember that the vapor pressure of salty water is going to be lower no matter what temperature I pick. So what will happen is if you made a graph of that, this red line would be the vapor pressure of salty water, and it's always going to be lower. And if you look at this and you said, oh, what's the boiling point for this particular salty water, we have to find the temperature where the vapor pressure of the salty water equals 1 atmosphere. And if you look, it's a little bit to the right of pure water, which means it's a little bit higher than 100 degrees Celsius. And this is just another way of saying that the boiling point of salty water is going to be higher than the boiling point of pure water. And it's not just the boiling point curve, this red line that shifts a little bit compared to this blue line. The freezing melting line, that looks a little bit screwed up. The freezing melting line also shifts, and it shifts to the left. And so what this means is if you have salty water, it's also more difficult to freeze compared to pure water. And what this means is the freezing point for salty water is lower than the freezing point for pure water. And so if I had some salty water, the freezing point for my salty water would not be 0 degrees Celsius the way that it is for pure water. It would be a little bit to the left, which would mean it would be a little bit lower. So it might be -2 degrees Celsius or something like that. And if I put more salt into my water, then the freezing point would go down even more, and down even more, and down even more. And if I put more salt into my salty water, the boiling point would go up even more, and up even more again. And those are called colligative effects. So these effects on boiling point and freezing point, when you throw something that is non-volatile, like table salt, and dissolve it in water, these effects have a special name. Because the boiling point of salty water goes up compared to pure water, the effect is called boiling point elevation, because the boiling point of the stuff of salty water or sugar water or anything else that's non-volatile dissolved in water goes up compared to pure water. It's an elevation of the boiling point. The abbreviation for boiling point elevation is this thing over here. This triangle is the Greek letter delta. And in sciences and in math, a lot of times that means change. And T just stands for temperature, and the subscript of B means boiling. So this little bit here just means the change in boiling temperature. And that's called boiling point elevation. And so the idea is this is a number. This is how much the boiling point of your stuff goes up. And the amount that it goes up depends on how much stuff you dissolved in the water or in whatever liquid you're interested in. It doesn't just have to be water. So if the new boiling point of my salty water was 102 degrees Celsius, then the boiling point elevation would be 2 degrees Celsius. But if I threw more salt into the water and the boiling point went up even more, and maybe the new boiling point was 104 degrees Celsius for my really salty water, then the boiling point elevation here would be 4 degrees Celsius. And there's another special name, and that is, since we said that if we add salt or something else that's non-volatile to our liquid, like pure water, that the freezing point goes down, that has a special name. It's called freezing point depression. And this is also a number. So again, the Greek letter delta, which means change, T means temperature, and F is for freezing. This is how much the freezing point goes down. If I had some salty water and the new freezing point was -2 degrees Celsius, then basically the freezing point depression for my salty water would be -2 degrees Celsius. Or if I added even more salt or something else that made the freezing point go even down farther, maybe to -5 degrees Celsius, then the freezing point depression would be -5 degrees Celsius. And all of these, again, are called colligative effects. And both of these things, the amount that the boiling point goes up or the amount that the freezing point goes down, are controlled colligatively. And again, what that means is, it doesn't really matter what I dissolve in. The effect is just controlled by how much of the stuff that I dissolve into the liquid. Freezing point depression also explains why we put salt on the roads during the winter time up in the Northeast, and that is because we are trying to prevent water from freezing on the roads and making them more slippery. And the way that you can do this is if you throw enough salt onto the roads, it will make the freezing point of water go down, and that means it'll be harder for that water to freeze. So under conditions where pure water might freeze and make the roads really slippery, if you throw enough salt on, it might not freeze at all, and so the roads would be less slippery. And that's basically what the point of putting salt on the roads during the winter time is, or salt on your driveway. That's the introduction to colligative effects. We are going to spend the next couple of videos talking about how to estimate what the boiling point elevation might be for a liquid, or what the freezing point depression might be for a liquid. I remember when I lost my mind. There was something so